Hi guys, we've got a very chill video for you today. Today we want to discuss double integrals with polar coordinates. So if you recall from the last set of videos, we discussed how we could take a volume under a function. So we defined, we had an xy plane, like that, and we could define a region. We could define a region R or something, and then we would want to look at some sort of function that lies above R that, I don't know, looks like that or something. I don't know. Maybe that has some depth, and that's F. We want to find the volume underneath this solid, or underneath our function, right? Now, R, our region, has usually been defined either as a Cartesian product, so this is where we have the integral between a and b, then the integral between c and d of f dA. But we also discuss general regions where maybe we have, I don't know, one side is a function like that and one side is a function like that, and this is our region. And we figured out how we could integrate by either taking that as a type 1 region or a type 2 region. But now we can also have some other more funky sort of shapes. Like if you remember back from earlier videos in single variable calculus, how we could define all of these weird polar curves. Now, the easiest polar curve obviously is a circle. So say I want to set this region as a circle, it would be hard to define that as a type 1 or a type 2 region. But instead of taking our integral using dx and dy differentials, we can use dr and d theta differentials from polar coordinates. Now, I'm not going to go through a full derivation. There is a geometric derivation, which I find a little bit time-consuming, that kind of goes through the area of a sector and tries to do a double Riemann sum. But at the end of this unit, we're going to come across something called the Jacobian Matrix, and we're going to see that our polar differential is a little bit strange, and we will do a full derivation of why it is that way when we cover the Jacobian matrix at the end of the unit, and I find that to be a far more elegant solution than the geometric solution that we could discuss now. Anyways, so before we get into actual examples, which we'll do in future videos, why don't we look at just a review of polar coordinates, just because that's something I think we're going to need, because we haven't really been using them recently. We've been doing a lot of parametric equations, we've been doing a lot of derivatives and integrals, but we haven't been doing much with polar coordinates. So if we remember, we have the Pythagorean Theorem. So if I have r squared, that's going to be equal to x squared plus y squared. So if I define a polar coordinate system, I have r here. I can project that into x and y, and I have some theta, and then here I have some r vector, or not a vector, but just a length. You can obviously use the Pythagorean Theorem, since this is a right triangle, since we're dealing with an orthonormal basis of x and y. We can also define x and y from r's and thetas such that x is equal to r cosine theta. That should make sense with the diagram. And y equals r sine theta. Again, that should make sense with the diagram. Now again, we've been dealing with Cartesian products where we've had R as a domain defined by a set of ordered pairs x and y, where x is between either a function or some constant. Let's just keep this general. We have f sub 1 of x is less than or equal to x is less than or equal to f sub 2 of x. Oh wait, no, let's just do it with constants. We have x, a is less than x is less than b, and then c is less than y is less than d. And that's how we've defined these regions. Now we can define them also with polar coordinates. So we can define a region such that a radius, we have a certain radial value. So let's say our radius is defined between here and here. So these are constants like a and b. And then we also have an angle defined. So maybe this is our angle here. This is our angle theta. And this will sweep out this kind of sector here. So we'll be dealing with this. So this will be our region, no? So we can kind of deal with that. And then if we replace a, b, alpha, and beta with functions, then we can come up with some crazy regions that work nice with polar coordinates. And again, this will come up later in the Jacobian matrix, but sometimes we could be given an integral that it looks like they want us to do it in Cartesian coordinates or rectangular coordinates. But later we might say, hey, this region actually, it would be easier to integrate if I parameterize this function with respect to r and theta as opposed to x and y. I'm going to switch to polar coordinates. That's going to make my life easier. You can always make that decision. That's what's great about multivariable calculus. There are a lot of paths you can go down when doing these types of double integrals, and especially with triple integrals later on where we have more coordinate systems. You really have the freedom to choose where you want to go. Anyways, let's just cover what the actual double integral will look like when we perform this. And this is kind of where the Jacobian term comes in, but again, we'll cover that in the next video or later videos. So if I have the double integral over a region of f of x and y with respect to some differential area, I know that I have a set here such that x is equal to r cosine theta and y is equal to r sine theta. So obviously we can say that our integral is going to be over the same region r of f of r cosine theta, r sine theta, right? So we replace all of our x's with r cosine theta, and all of our y's with r sine theta. And then at the end, we have r dr d theta. Now, this r is the weird Jacobian term, but again, we'll cover that in a later video. Thanks for watching. That was a quick intro to polar integrals, or polar double integrals. In the next video, we'll do some examples, cover some more properties. And after that, we'll finish off double integrals with some applications, and then we'll move on to triple integrals. Thanks for watching. We'll see you guys in the next video.